Hello. In this video, we'll break down the topic of crystal structures so that by the end, you'll have a better understanding of what they are and how we describe them.
Crystal structures are defined by a lattice and a basis. A lattice is a regular arrangement of atoms in space such that the environment of each atom is the same. Each point in the lattice has a set of linearly independent vectors which define its position as shown in this diagram. Within a lattice we have things called unit cells. Unit cells are parallelepipeds whose corners are lattice points. There can be more than one unit cell within a lattice and they aren't unique. A unit cell can be described as primitive if it only has one lattice point and therefore is the smallest unit cell possible. The atoms in a unit cell define a basis. Each atom's position is described by fractional coordinates. For example, an atom in the centre of a cell would be defined by coordinates a half, a half, a half, since you need to go halfway along each axis to get to the centre. Using a lattice and a basis, we can now define a crystal structure. Miller indices are used to describe a plane intersecting a unit cell. They are always described by whole integers and can never be fractions, so you must multiply through to ensure you have whole numbers. As shown here, the plane intersects the x-axis at 1 over h, the y-axis at 1 over k, and the z-axis at 1 over l. The Miller indices are then HKL, written without commas, as shown here. If a plane is parallel to an axis and so does not intersect it, the Miller index for that axis will be 0.
The packing fraction, or atomic packing factor, is the fraction of volume in a crystal structure that is occupied by constituent particles.
The formula for the packing fraction, or atomic packing factor, is the number of atoms times the volume of atoms all over the volume of the crystal. As mentioned earlier, an FCC crystal has one atom in each corner and one atom in each face.
One thing to note is that the corner atoms, shown in black, do not belong entirely to this cell. In fact, in 3D space, these corner atoms are shared amongst 8 different cells. If you can imagine, there would be one cell on that side, one going this way, one going that way, and so on. Same goes for the face-centered structures shown in blue. These are shared between one other cell. So for the total number of atoms that belong entirely to this unit cell, that would be done by the following formula.
Okay, so we have the number of atoms is equal to 8 corner atoms multiplied by their contribution to the cell, which is 1/8, plus 6 face atoms multiplied by their contribution to the cell, which is 1/2. And that equals 4 total atoms in this unit cell.
Before we can calculate the packing fraction, we need to make a few assumptions.
Okay. So firstly, we assume that the unit cell is occupied by hard spheres. And secondly, we assume that the nearest neighbour atoms touch.
We now have our Na value. To calculate our APF, we now need our VA and our VC values. To do this, we will start by defining the lattice parameter, which in this example is just the side of the cube. We will call that A. Also, we will define the radius of each of our identical atoms, and we will label this capital R.
So the first thing to do is to calculate the combined volume of the atoms in the cell. From our assumption that atoms are hard spheres, we know that the volume of one atom is equal to 4 over 3 pi r cubed. And this means when we multiply it by the number of atoms, we get NaVA is equal to 16 over 3 pi r cubed.
We see from our previous diagram, which was the entire unit cell, which was a cube, and from our diagram here, which is just the face of the unit cell, we see that the volume of the unit cell is just A times A times A, also A cubed.
Okay, so now we have a problem. Our VA is in terms of R, and our VC is in terms of A. In order to simplify our calculation, we need to find a relationship between A and R.
This can be done easily by looking at our diagram and looking at the triangle over here. We can see that for R, across the diagonal is equal to, from Pythagoras, the square root of a squared plus a squared.
Okay. And after a few lines of simple working, we find that a is equal to 2 times the square root of 2 multiplied by r.
Okay. And subbing this back into our equation over here for the packing fraction, we find that 16 over 3 pi r cubed over a cubed, and subbing in our a value, 2 root 2 r cubed. And we can notice right away that the r cubes will cancel, and putting this into our calculator, we'll get 0.74 for the packing fraction of an FCC structure.